Well, congratulations on finishing your simplified RISC-V CPU core. What we're going to do now, if you've got time to complete this part, is to actually pipeline your RISC-V CPU core. So this is the design that you've built so far. And most of the pipelining I'm going to walk you through myself and show you how pipelining works with TL-Verilog. And then I'll leave a final exercise for you guys to do yourselves, and that'll be the register bypass or register forwarding logic. So the steps that I'm going to do first is, first of all, we're going to put your design in the context of a pipeline. And then we're going to distribute the logic across pipeline stages. So this is the code that you created, or it should be very close to it. So you should be familiar with this. This is the sum from 1 to 9 program, and this is the CPU that you guys created, next PC logic, fetch, instruction decode, etc. All right, so the first thing that we're going to do is to put your CPU explicitly into a pipeline. We're going to call that pipeline CPU. And initially, we're going to put all the logic in stage 0 of that pipeline. I'm going to select all of this logic and control right brace to indent that logic under stage 0 of the pipeline. I'm going to compile that. Let's organize our workspace a little bit here. All right, so that compiled successfully. And we can see now that we have a CPU pipeline. We have stage 0 in that pipeline, and that's got our CPU logic. And really, we haven't changed anything. This is the same design that we had before. Before we didn't explicitly provide a pipeline. In TL-Verilog, all logic is actually in a pipeline. And if you're not explicit about it, that logic will be in a default pipeline in stage 0 of that default pipeline. So we really haven't made any change here. But we're giving ourselves context to manipulate the logic within that pipeline. So the next step, now that we're in a pipeline, just to jump back to the slides for a second for context, now we have this. All of our logic is in stage 0 of this pipeline. And we're going to increase the depth of our pipeline. We're going to distribute the logic across stages of the pipeline. So looking here, our PC mux, or next PC logic, is in stage 0. And then we have the instruction memory, so fetch, and the decode logic, and PC increment, all in stage 1. So let's do that first. So here's our PC mux in stage 0. Then let's put some logic in stage 1. So we have our fetch logic, instruction memory. We have decode, decode. This is all decode logic up to here. So at this point, we're going to stage 2. But there's one little piece that we're missing here, which is this increment. That used to be in stage 0, and it actually used to be coded as part of the PC mux. So let's explicitly pull that to stage 1 as well. So that increment logic is here. And let's create an expression for that. Incremented PC. And that's 32 bits. So the incremented PC is the PC plus 4 for binary 100. And then our PC mux, in the default case, is going to select the incremented PC value of the previous instruction. Okay, so this is now logically same as it was before, but our increment is in stage 1. Now the register file read logic is in stage 2. So is the, let's see, that would be the branch target calculation. So let's check that one. So this is all register file read. Branch condition, branch target. So I guess we'll leave this here in the program. We can specify the stages out of order. That's perfectly fine. So that's going to be in stage 2. And our arithmetic logic unit is in stage 3. ALU. So is the rest of our logic. So this is the branch taken determination and the register file write logic. So let's see what we've got left here. Here's our register file write assignments, and we can move those to stage 4. Just looking back at the slides here. Sorry, that would be stage 3, so that's in the right place. And branch condition. So everything looks good. Some of the logic we've provided for you in this shell, and that includes the register file itself and the instruction memory. So we've got some parameters here on this macro, the first of which is the timing for visualization, which I need to move to the latest stage, which would be 3. And the next one is the instruction memory, which is now in stage 1. Register file read, we're moving to stage 2. Register file write to stage 3. So the macro is going to take care of that part of it for us. And let's compile that and simulate. So we got a failure. We should check our log. So let's see. We have 2 errors here. First one is saying that we're trying to use the branch target PC before it's available. And the next one is telling us we're trying to use the taken branch condition before it's available. So what's happening here? Well, let's look back at our diagram. So what's happening is actually this. So we've moved our logic to different pipeline stages as we wanted. And in doing so, our logic, let's look at this case first. This is where our warnings come from, our errors in the log. Let's look at that logic for the PC mux. And we can look at it here in the log message. So our PC mux expression is, let's just look at each of the pieces here in detail, because this was logic that we provided for you. So first of all, we want to reset the PC to 0. We're going to start executing our program at 0. And the first cycle of execution that's not reset should be executing instruction 0. So, we want to assign PC to 0 for all of the reset cycles and the first cycle after reset. So we actually use this ahead by 1 reset, which says if we were resetting for the previous instruction, where there is no instruction in the previous cycle, but in the previous cycle, if we were resetting, then we want to be 0. Okay, and that covers all the reset cases and the cycle after reset. After that, we're either going to branch or we're going to increment the PC. Now, the branch, we want to branch if the previous instruction was a branch and that branch was taken. And that's our taken branch condition. So this says if the previous instruction, so the instruction that is ahead by 1, okay, so the branch from the previous cycle, or more accurately, the branch that is ahead of us in the pipeline by one pipeline stage. Okay, and that's the use of the ahead by one operator. Then we want to assign the PC to the branch target of that branch instruction, which is the previous instruction. So that's the use of the ahead by operator to reference the instruction that's one ahead of us in the pipeline. Well, the way we changed our design, right, we're trying to do our PC mux here. The instruction that's one ahead of us in the pipeline would be here in stage 1. In stage 1, we haven't yet calculated the branch target. Right? That determination is done in stage 2. So really what we're trying to do is access this branch target before we've assigned it. Okay, so it's almost like we've implied these negative flip-flops to go back in time so we can grab this signal we haven't computed yet. Obviously that's a problem. We can't implement a circuit like that. And so it can be instructive to understand the scenario by looking at what's called a waterfall diagram. The waterfall diagram is showing how instructions are progressing through the pipeline over time. So we're looking at the execution of 5 instructions here in subsequent cycles. So the first instruction, the add, goes through its next PC computation, which is at 0 in our case. The decode, which is at 1 for us at the moment. The register file read at 2. Execution, which is at 3. So this is the arithmetic logic unit executing the instructions. And the register file write, which actually I believe we're doing in stage 3 as well. So this diagram isn't exactly what we're implementing. But you can think of the register file write stage as being the stage at which we want to consume the register value that was written. So we're looking first at this branch determination, the PC determination for the target of the branch. So let's look at this third instruction here, which is a branch less than. All right. So we've got a few instructions in the pipeline. This first instruction, the add, has reached its execute stage. The next instruction is at its read stage, one stage behind it. There's the pipeline up here. So, at this moment in time, this vertical column, we have the add and the execute. We have the add-I behind that in register read. We have the branch less than in its decode stage. Okay, so these instructions keep marching through the pipeline, one cycle after the next, and when the branch less than gets to its execute stage, that's when we calculate the target of the branch and determine whether the branch is taken. Only at that point can we actually redirect the PC to the proper location. What we're trying to do at the moment is execute the target of the loop the next cycle. Okay, we don't know that target yet, so we can't do this. What we have to do instead is this. So we've assumed in the front end of the machine for the next PC logic that we're fetching the next instruction sequentially. So there are a couple instructions behind the BLT that we fetch. These were the wrong instructions, so we refer to these as bad path instructions. And when we get to the execution stage for the BLT, we determine that these are bad path. We squash them, meaning we avoid writing their results. And we redirect at that point the PC to the correct branch target PC. And then we fetch the branch target, the add here. Okay, so next I'm going to walk through that change to fix the timing of our design and implement this, what's termed a branch shadow. So let's go back to our logic here. So the first thing I'll do is fix the broken timing. Right? So the timing that we actually want for this taken branch is to access the taken branch from the instruction that's 3 3 stages ahead of us in the pipeline. Okay, so if the instruction 3 stages ahead is a taken branch, use its target. And that addresses the 2 errors that we see here in the log. So let's compile that. And look at our log. Strange that the diagram failed, but sometimes this diagram generation can fail. Okay, and so let's look at the visualization. It seems like everything's running good. Let's also check, the log says we passed, which also is surprising actually. But let's take a look at the visualization and see what has happened here. So we have first couple cycles where these are essentially reset cycles. So actually in this macro instantiation at the bottom, we've changed the timing of our visualization such that the visualization is now reflecting stage 3 in our pipeline. So this is all telling us what's happening in stage 3. So we have 2 cycles that are essentially reset cycles. And then on the 3rd cycle, we fetch the first instruction. And let's see what happens when we get to the branch. So here's our branch. And we continue on after the branch. And then we go to the branch target. So this instruction is the branch target. And we correctly, now with the 3 cycle delay, have redirected the PC. But if I step backwards to the branch again, the cycle after the branch, we're doing the add instruction. And we see that the add instruction is doing its thing and writing a result, as is the next instruction, which is in our case garbage. And somehow miraculously the program has resulted in the correct ultimate register value that we're looking at for success, but that was kind of luck. So let's correct the behavior here so that these instructions actually are treated as garbage instructions. So what we need to do to treat them as garbage is to make sure that they have no impact on the state of the machine. And the only state that we have in our simplified CPU core is the register file. So the result of the instruction being written and stored in the register file. We need to make sure that these bad path instructions don't write the register file. So let's find the register file right. Register file read and write. So here's where we are determining whether to write the register file. This is the register file write enable. So we need to change this expression to avoid writing the result to the register file if we're on the bad path. So we're on the bad path if the previous instruction was a valid taken branch instruction, or the previous instruction was a valid taken branch. So how do we code that? Well, let me just translate that English statement into code. So we are going to write the register file if we have a valid read destination and well, let's just do it this way. And this is not and this is a valid instruction. So I have, this is actually an added expression that you probably don't have in your code. So this is saying, this is reflecting the behavior that was originally in the code, where as long as we're not on a reset cycle, every instruction is a valid instruction. Okay, and valid is not used anywhere, but I have added it here to the visualization, so I needed to add the signal. But now we need to determine whether the instruction is valid, and that's the expression I just explained, right? That's the expression here for this new red logic. Okay, so the instruction is valid, and we'll write the register file if it is not So it's reset, and it's not a, oh, let's not do it. All right, let's do, and it's a valid branch instruction. Actually, let's do valid taken branch. This is the previous instruction was not a valid taken branch, and the previous instruction was not a valid taken branch. And I'm just using this valid taken branch before I've assigned such a signal. So valid taken branch is a taken branch instruction that is valid. Well, this seems a little cyclic here, doesn't it? Valid is dependent on valid taken branch, and valid taken branch is dependent on valid. This is actually correct. I'm going to go ahead and compile this and take a look at the logic. The reason it's correct is that because of this ahead by one. So this is looking at the the valid taken branch of the instruction that's ahead by one and ahead by two. So we're looping back through a flip-flop for these expressions. And anytime you have this sort of cycle through a flip-flop, that kind of triggers something in your mind that there's state here. So we're actually remembering the sort of validity of the previous instruction. That affects us going forward. And anytime you have something you're remembering, some state in the machine, that's a good indication that you need a reset as well to get your machine into a known state. And we do that here by ensuring that we're treating instructions as invalid during reset. Okay, and you can think about this logically. If we didn't do that, we don't know what's happening before reset. We're in an unknown state, and who knows what's happening when we come out of that. Are we in the shadow of a branch or not? So by forcing instructions to be invalid during reset, we address that. All right, so we have our valid condition, and that's based on whether we're in the shadow of a taken branch, and we're using that valid, and I'll explore that here in the nav TLB. Let's find the valid, and we're using that valid to control our register write enable. So let's see what's happening now in the visualization. I'll step back to cycle 0. So here's our first instruction. We step through. Let's see what happens when we get to the branch less than. So the next instruction after the branch less than is an add. That add is invalid. The visualization reflects the invalid status of the instruction by turning it gray. And we also see that that invalid instruction is not writing back anything to the register file, and that's due to this conditioning. So this looks good, and now we do branch to the target and continue execution. And again, enter the branch shadow, invalid instructions, not writing the register file, and so on. And let's see if we pass the simulation here. We failed. So why did we fail? I'm not actually sure, so let's step through. Make the visualization a little bigger here. And we see our values incrementing. So this is our sum here, up to 15, 21, 28, 36. Should get to 45, which is our end condition. And we fail to, or we take another branch, which we should not take. Then we end up with 55. All right, so why did we branch here? Okay, so this is where your part comes in. We failed to branch. Let's look here. So back at this branch that should be taken, we should be checking R13, checking R12 versus a value 10. Oh, that's the target, sorry. R12, I think, is the value of 10. R13 is the sum register. We're comparing them and reading the value. We should be at a count of 10. Sorry, R13 is not the sum, it's the count. So our count should be at 10. We see a count of 10 here in R13, but it's read as a 9. Let's step back and we execute the BLT. We read 9 even though the register file contains 10. So something's goofy here, and what's goofy is actually, if I step back a few slides, it's this case here. So in addition to breaking this path, we also, now that we've stretched out the register read and the register write, this also is another hazard. This is a read after write, and there's nothing broken in the design other than the fact that we're trying to do too much in a cycle. So we're going through the arithmetic logic unit. We're determining the value to write and immediately using that value that we write into the register file, or not necessarily that value, but we're using the state of the register file as updated by this instruction to read for the next instruction, all in the same cycle. And it's not realistic at a high frequency to do all of this in a cycle. Why are we functionally broken, though? This picture here is not actually functionally broken, but actually when we change the instantiation of this magic macro down here to say we want to read in cycle 2 and write in cycle 3, stage 3, what that macro actually implemented for us was actually this picture, which is what we want, where we're reading from the register file with a 2-cycle latency. And actually, this is drawn wrong. Let's fix that. Okay, so this is what we've actually implemented. All right, now, having implemented it this way, this means that one instruction writing a value in the register file can be followed by another instruction that is reading the register file before it has access to that write value. So let's look at the waterfall diagram to understand that. Right, we have this add I, for example. This isn't the same as our sum to 10 program, but similar instructions here. So this instruction, the add I, is writing to A3 and reading in the BLT from A3. So the write's happening in the write stage, or rather the write stage is where we're reading the written register value. Right, let me just jump over here. Again, Let me fix this. So, well, we're reading the register file that reflects values written by the instruction in its stage 4. So how are we going to fix this, right? So what's the case that's broken, right? The case that's broken is that we have one instruction followed immediately by another instruction that is reading the result written by that previous instruction. So it's this case where we have this backwards dependency of one instruction writing the register file and the next instruction reading the register file. So here what we're actually reading is the value in the register file that's updated by this instruction, not this one. Right, so the case that's broken is this one, right? Specifically where the first instruction is writing the same register that is read by the next instruction. So we can keep this read loop as it is. We need it this way to be able to implement this logic and then fix the case that we're talking about. In other words, bypass the register file. Or another way to say that is forward the result from the ALU to the next instruction. So this is called either register file bypass or register forwarding. So that's the only remaining piece in this design to get to a successful running program. And this piece is for you to implement. So not this piece, this piece. So you'll implement this register file bypass path. And to do that, you can start with the code as I've left it. To do that, go back to the repository where you started. Hopefully you've still got the link for that. So that's github.com, Steve Hoover, ChipEXPO 2021. So there's now a link for part 2 starting point code. That's the code as I've left it at this point. And again, you can right-click on that, open that in a new tab, and that'll bring up MakerChip with the code as I left it. And we'll just wait a minute for that to load. And if you scroll down, so here's where we're assigning the source values for the arithmetic logic unit from the register file. And you will update that logic to insert this mux, these two muxes. So those two muxes are going to either select the value from the register file as it was, or the result from the arithmetic logic unit, the previous cycle. So select the previous result if it was written to the register file, and if the previous destination register matches the source register for this instruction. Okay, so I've underlined previous here. Make sure you're getting your ahead by operators correct to implement this mux, grabbing information from the previous instruction one cycle ahead. Okay, and when you implement that logic, if it's working correctly, you'll see a passing message in your log. And that'll wrap things up. So you can pause the video here. You can take your time to implement the logic. And when you're all done, you can start up this video again and I'll just wrap things up.